long human history, and with the development of present technology, several number systems with different bases or radix have been developed for specific purposes. It is interesting to note that over a period of time, following bases of number have been developed to satisfy the different objectives: 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16, 18, 20, 23, 24, 26, 27, 30, 32, 33, 36, 52, 56, 57, 58, 60, 61, 62, 64, 85, 91, 92, 93, 94, 95, and 256. For this course, we would focus our discussions on two most commonly used number systems with bases of 2, which is called as binary, 8, which is called as octal, 10, which is called as decimal, and 16, which is hexadecimal. Let's see the number system chart. This is the chart of number system which we are going to discuss in this course. Decimal number system is the most used number system by humanity. Decimal system is a base 10 system which uses the number from 0 to 9. Binary number system, which is the base 2 system, is being used in digital electronics due to representation of on and off state of transistors by 1 and 0 respectively. Hexadecimal systems are base 16 system which uses numbers from 0 to 7 and A to F for the representation of hexadecimal numbers. Octal numbers are using the base 8 for the representation of its numbers. It uses numbers from 0 to 7. The details about these number systems we would be covering in the coming chapters. We will also learn about the mathematics involved in it and solve related problems to get the experience in these number systems. By the end of the course, we would be comfortable with each one of these number systems and would be able to solve problems related to decimal, binary, hexadecimal, and octal number systems. Let's see the concept of base or radix. In mathematics, the base or radix is a representation of the number of unique digits, including 0, which are used to represent the numbers in a positional number system. For example, in decimal number system with base 10 uses 10 numbers from 0 to 9 to represent all decimal numbers. Similarly, in binary systems with base 2 uses only 2 digits, 0 and 1, to represent all binary numbers. Generally, in decimal systems, we do not write base as it is the most commonly used number system in the whole world. Any number written without any base is assumed to be a decimal number with base 10. In the case of hexadecimal numbers, which have the base 16, uses 16 numbers from 0 to 7 and A to F to represent all hexadecimal numbers. Finally, in the case of octal numbers with base 8, uses its numbers from 0 to 7 to represent all octal numbers. Now, it's very important to understand why the base or radix exist. Understanding the concept of base is very important as it completely changes the number with which it is attached. For example, 101 with base 10, which is decimal, is different number from 101 with base 2, which is binary, which when converted to base 10 decimal would be equal to 5. Simply put, 101 in binary is equal to 5 in decimal, which is also equal to 5 in octal and also 5 in hexadecimal. Let's look at some more examples to get the complete understanding about the concept, including both octal and hexadecimal numbers. To understand these examples, let's look at the first one. 101 with base 2 in binary is equal to 5 with base 10 in decimal. And it is also equal to 5 with base 8 in octal and with 5 with base 16 hexadecimal. Now that does not mean that what is equal to 5 is the corresponding numbers are same. Let's look at the second example. The binary 100111 with base 2 is equal to 39 with base 10 in decimal, and here the things are different. 47 with base 8, which is octal, and 27 with base 16 in hexadecimal. Let's look at one more example. 1001100 with base 2 is equal to 76 with base 10 in decimal, and 114 with base 8 in octal, and 4C with base 16 in hexadecimal. Now, what is hexadecimal? We can say that it is a shorthand of binary. The hexadecimal systems are often used in computing because of their ease as a shorthand for binary. Every hexadecimal digit corresponds to a sequence of 4 binary digits, since 16 is the 4th power of 2. For example, number 7 with base 16 would be equal to 0111 with base 2 in binary, while 8 with base 16 would be equal to 100 with base 2 in binary. This means that 78 with base 16 would be equal to 0111 and 1000 with base 2 in binary. That is the reason hexadecimal numbers with base 16 are the shorthand for binary numbers. 78 with base 16 can be represented with only 2 digits, while in binary it will require 8 digits. A similar representation and relationship holds between every octal digit and every possible sequence of 3 binary digits, since 8 is a cube of 2. Let's look at the next shorthand of binary, which is called as octal. The octal systems were previously used in computing because of their ease as shorthand for binary. Every octal digit corresponds to a sequence of 3 binary digits, since 8 is the 3rd power of 2. For example, the number 1 with base 8 would be equal to 001 with base 2 in binary, while 7 with base 8 would be equal to 111 with base 2 in binary. This means that 170 with base 8 would be equal to 001, 111 and 000 with base 2 in binary. That is the reason that octal numbers with base 8 were used as the shorthand for binary systems. 170 with base 8 can be represented with only 3 digits, while in binary it would require 9 digits. Decimal to binary, hex and octal conversion. We will cover in detail about these conversions in the later part of the course. For now, let's understand the basic concept behind it. A repeated division and remainder algorithm can convert decimal to binary, octal, or hexadecimal. It means divide the decimal number by the desired target radix, that is 2, 8, or 16. Append the remainder as the next most significant digit. Repeat until the decimal number has reached 0. In simple language, it means that we need to repeatedly divide the decimal number by the base or radix. For example, if the decimal number has to be converted to binary, then it should be multiplied by 2. Similarly for hexadecimal and octal with 16 and 8 respectively. We need to write the remainder of each division till we can divide no more. Writing all remainders from the last to first would give us the desired number. We would see this in action in further chapters of this course.